All right. I hope everyone's doing fine so far. Um, and I hope that everyone is preparing. Everyone is preparing well on their exams. So I'm going to go to my whiteboard. What is happening to my whiteboard? Oh, oh yes, I am loving it. I'm not going to give feedback though, because I don't really care. Um, Let me go ahead and see if I can like get the whiteboard booted up. If the whiteboard can't boot up, then I guess I'm gonna have to like do it some other way. But for now, uh, hopefully this works fine. Okay, let's see here. Let me close off a few things before we do that. This should be gone. There you go. Okay. Um. Oh my. Okay. There you go. So, let's see if scripting works. Yes. Okay. Um, you might notice that like my video can be a little bit slow. I might also actually make my webcam a little bit like more optimized or something. I don't know. But regardless, if you find out that I'm lagging or something like that, then that might be because of my computer like being a bit slow today. So, Um, without further ado, let's begin. Um, in case you all are new, my name is Caleb. I have I am also in the software stream of computer engineering here at Toronto Metropolitan University. This tutorial is for reviewing concepts in CPS 688, which is Advanced Algorithms. So our agenda today, if I can dig up my notes on Microsoft Word, is as follows. So first, let's see if I can write here. First, we're gonna work with dynamic programming. Not sure what's happening with the whiteboard, but oh well. So I'm going to erase that. Okay. So first, we're gonna review on dynamic programming because I've heard that it's gonna be on the exam. Second is I'm going to also take a look a little bit at divide and conquer. Then we will look at NP complete, basically the most basic things that you're gonna need to know about them. Not too much though, hopefully. Then, scrolling down on my notes, we're gonna work with network flow. My words may be a little small, so I will zoom in just a little bit. Okay. Then I'm going to cover substring search. And finally, oh, actually, no, there's more. There's linear programming. I think I should have like made this tutorial last for 3 hours, but it is what it is. Maybe next time I will take a look. I will reevaluate like how much time I need. Then lastly, um, we will talk a little bit about randomized algorithms. Oh, come on, dear whiteboard, why are you not working? Oh goodness, the whiteboard's performance is a little bit bad today. So, uh, give me a moment. What happened to the whiteboard? Oh, well, that was embarrassing. Okay, so these are going to be the things that we're going to cover because they're going to be on the exam. So I'm going to start with dynamic programming. Okay, so let's begin. So I'm going to scroll here. So dynamic programming Oh my goodness. Sometimes I really don't like how laggy my things are. I might even need to like restart my devices a little bit. Okay, let me see. Okay, so dynamic programming. So dynamic programming. So dynamic programming is a family of algorithms solve where you solve a particular problem by solving perhaps like the same overlapping problem with smaller inputs, and then you can like do stuff to them, like adding, subtract, compare, and you might also think about like how is this even different from divide and conquer. It is the fact that dynamic programming, although it involves splitting the problem into pieces, it breaks down the problem at every single possible point.
laptop Zoom कर लो ना.
Oh, is there a Zoom problem? Yeah, what happened?
Oh, sorry, I was my mic's muted.
Ha, okay, sorry. It's okay, no worries. Um, yeah, so as long as we don't have any weird Zoom problems going on, I'm just gonna keep going. And yes, if I'm pretty laggy, I might actually just like just stop my like filter and it might be because I'm using like the weird like chroma key filter, which actually is pretty much lagging me out. Um, just give me one moment because I might need to do some changes. I might need to make some changes here and there. Filters. I'm not gonna do background removal, nor am I gonna do chroma key anymore. Ugh. Ugh. Well, looks like I'm forced to like just show you my bedroom now. Okay, so does this help out in the video side of things, everybody? Okay. So as long as you all find it fine, it's less laggy now. Okay, we should be able to move forward. Maybe the rest of the lag is because of network latency and stuff. You know how it goes for like internet networks and network flow and stuff. Okay, so dynamic programming, like I said, you basically you want to um you want to solve some big problem by splitting them into every possible piece. I might call it a screen. So we take the solved piece, and then we're gonna combine it with some other piece. For example, I solved this small piece in green, and then I'm going to combine that with like a soon to be solved piece in purple, and then I'm going to do my third unknown pieces in orange. I'm going to color that slowly, so give me a moment, people. So I'm going to use orange to color like the new pieces that are built on top of our previously solved pieces. So note that each new piece is represented by different colors. And finally, we will eventually get to our target problem, and I'm going to color the rest of this in blue. So basically, these are the newest pieces, and then our previous piece, the piece that deals with the 3 by 3. So we got the yellow side, and then the purple pieces, and the green pieces. So what we're doing here is that because our because like perhaps the nature of this problem is that like we can solve like uh some kind of uh how to say it, because like the definite because I don't want to use the definition overlapping subproblems, but that is a commonly used term. So we're solving a problem that's by like taking in like smaller inputs and applying algorithms using our previously solved solutions using those smaller inputs, for example the green pieces, and then we slowly build things up. There are different ways you can do dynamic programming problems. The two and like there are two directions you can take with this generally. One is doing it top down. Top down means like you start big. Um, so top down. Oh, I should have used my pen to change the color. So top down. If I can find where my thing is. Oh my. Um, Give me just a moment. Okay. So top down. So the directions you can solve dynamic program problems in includes top down. I'm scrolling down now. For people who want me to scroll back up or something, just let me know, please. Okay. And so top down means you start from a big piece. For example, I'm going to split it. I'm going to do something like some problem at 10, and I'm going to use I'm going to get the solution to this problem by splitting up by splitting up our by splitting up our problems into perhaps like two pieces like this. We may also call different ways different splits. So basically, we may also call like f of 1 and then f of 9, something like that. And then they can continue from there as well. And then from 8 and 2, they can also call from maybe 3 and 5. So basically, we're trying pretty much every feasible input, every feasible combination of input. And because if we're gonna do it top down, sometimes you may encounter repetitions, something like that. It's very laggy now. If you're seeing the whiteboard and it looks like it's laggy, it's actually how whiteboard works. It's kind of like Google Docs. Yeah, but if it is laggy to you, then yeah. Um, I don't think there are any weird issues to me though. But do let me know if like at least my face cam is like really bad. Yeah, but for the whiteboard, I cannot do anything to it because like that's how like it captures changes like in real time. Yes, so looks like it's good. Okay, I'll keep going. So you'll see that like if you have to break this down so many times, you may encounter that's like if you break this down recursively using the top-down approach, you may actually deal with an exponential time like O of 2 to the n, which is pretty bad. Like, not gonna lie, this is definitely bad. Um, So one way we can make sure that we don't deal with these repetitions, like you have a we have like a whole lot of repetitions that should not be repeat that we should not repeat at all. So the way we so a lot of times the way we deal with like unnecessary repetitions in this type of problem is to use something called memorization. And that is when where we record our results in some data structure like an array. For example, this will store f at 0, this will store f at 1, this will store f at 2, and so on. For example, if I have something like this, um, if I have something like this, then the algorithm can just look up the stuff from the memorization, and it will then uh, it will then not call the already solved subproblems, the already solved solutions using those inputs. For example, if I've already solved f of 0, then I can just look up f of 0, which is 1, and then I don't have to call it again. Another way you can do so, uh, we've already looked at some dynamic programming problems like coin change, where if I have to make change of $5, you can maybe have something like then in that case you have to maybe look at the minimum of how many coins you need. Uh, for example, if I have like a if I need to make a change of $5, I can I have to like take one of the one of the what is it, tokens, one of those coins. Well, it's called coin change. I have to take one of the coins. It could be any of the, for example, like $1, $2, a quarter, uh a dime, and a nickel, something like that. And then I'm going to take the minimum of the coin, the same coin change problem, but this time, since for example we've taken like $1, we have to like do the rest of the $4, right? Uh, Something like that, and then I can also maybe take $2. In that case, we solve for like the number of coins we need to make a change for $3, and then we can also do a quarter, take away a dime, or take away a nickel, like so. So in that case, we just take the minimum of all of these. So that's one example, coin change. Now another approach you all may have heard is called bottom up. Okay, so bottom up is where is the opposite direction, where like we start by like building it from like a really base case like f of 0, and then you solve f of 1 with f of 0, and then you just keep building up until you reach what you want. Okay, I'm going to actually move this um downwards so that like it fits pretty well. One problem you've used the bottom up approach with in your labs is called the rod the is the rod splitting problem asked by Microsoft. So that one rod problem where you try to split up a rod into different pieces, and those pieces will give you money. For example, this gives you $4, this gives you 3, and this gives you like, I don't know, like 50 cents, something like that. So you've done the bottom-up approach by perhaps, and to visualize like the bottom-up approach, I'm gonna take a rod, okay, of length 10, and then I'm going to start by taking a look at my possible ways to split the rod. Perhaps if I, perhaps what if I split by what is split a piece of length 1? Well, how much do I get? Well, well, if I just well, we look at like a piece of the entire rod, and we look at the possible ways to split the piece. So, for example, how about a piece of length 1? Well, we can only perhaps like split up one piece with, well, just a piece with length 1. So we just look at, for example, $1. So we look at perhaps like $1 for like a piece of length 1, and then we're gonna build our way to length 10. So now that we have like the optimal profit for a piece of length 1, let's look at the piece of length 2. We can perhaps cut a two piece. Oh, whoops. We can perhaps cut a two piece, but if a piece perhaps like costs like if a piece cost it gives you like only 50 cents, then like you don't really want that. So in that case, what about I cut a one piece again, but this time uh so this time we're gonna need to also look at how much we can how much money we can make by splitting the remaining piece. Okay, in our case, like we can make $1 with that, and that's pretty good. That's better than just making like 50 cents. So we can make a total of $2 by adding up the pieces here. Okay, hang on. By adding up the pieces here. So in that case, that would be $2. We're gonna keep on like building up. Like, so now we've dealt with like length 2. How about length 3? Well, we're gonna first chop up an entire length 3 piece. How much does that give you? Well, I don't know if it's the best way forward, so maybe let's try chopping up 2. Hmm. How much does that give you? For example, this gives you 2, and then um this gives you like this. If I chop up a 2 piece here, and then this will give you $2, and then this will give, and then like the remaining piece will give you 1. So I'm going to keep on like chopping up smaller and smaller pieces to test the limits until I'm not gonna draw all the lines here, until you get like enough something of until you reach length 10, and then you're gonna do one last experiment, and then you one last experiment on those pieces, and then you should be able to get your maximum profit by splitting up your rod. Of course, make sure, of course, the bottom-up approach will involve like filling up an array, perhaps of it may involve filling up an array of revenues per length, for example. You can do something like that. Yes, I know I made a Fibonacci sequence with this. Maybe I'll do one for length 0 as well. So basically, the bottom-up approach, you may also use an array to remember like your previous result, and uh, yeah, and that's why you can do it. You may even reduce the memory complexity if you need to, by just only recording the last one, the last result or the last two results depending on what you need. Okay. All right. So I'm going to move on now because we're actually losing a whole lot of time here. Um, so I'm going to now um, so that is a dynamic programming. I think it's best that you look at the lectures to see to learn more about it. There are a whole lot of applications for dynamic programming, and it also daunts people quite a lot. Okay, so are there any questions before we move on? Oh dear. Um, okay. I'm going to. We will be building a table to solve a coin change problem. Hmm. Well, sure, you can do that. You can do that. You can build up a table to determine like the minimum number of points you need to make a change of like $1, then $2, then three, four, and so on. Yeah, that's one way you could do it. Is divide and conquer used for anything in the course other than sorting algorithms? Or I said today there will be nothing based on sorting algorithms on the final exam. Good question. Actually, counting inversions might be on the exam, so you might need to study on that. Um, for divide and conquer, you're just splitting up an array of, for example, of 8 things. You're going to okay. Well, actually, I'm going to actually zoom in here because this is way too big. So for divide and conquer, you just split up an array of stuff, and then you're going to split them into equal chunks. You only do the splitting at a single point. Okay, for example, the midpoint between the array. Okay, only one single point. You don't have to do all the points, unlike dynamic programming. Then for the sub, for this little sub array, I'm gonna split them into twos like so, and then these will turn into one element arrays like so, and then we're gonna start combining them back, and then combine those combined subarrays, and finally do it one more time. Then you have then you have the whole, then you have like the entire solution for the entire array. So there are time for questions at the end of the study hall. Like I will do that. I will definitely try to make it to the Q&A because I'm not sure if like 2 hours would be even enough to cover all this stuff. So maybe I may need to brief on like a certain um on certain concepts. I will make a note for the divide and conquer. So for divide and conquer, you want to split at only 1 point. 1 point per iteration. Okay. So that's divide and conquer. You may want to look up some problems like counting inversions. That one's pretty cool. You may also look at like some other applications like merging merging k-linked lists. There's also one which I really love to do, and that's called common prefix. Basically, I'm gonna give you a couple strings. Um, and I want you to return the most common prefix. For example, in this example, it should be AB, not ABC, because there's the S that blocked the C. And the way I pretty much did it is that like first started by like looking at the common prefix between the first two, which should give ABC, and then I looked at the computed prefix with the third one, uh, which should give you AB. So yeah, you can actually do divide and conquer for common prefix, and that's a really really cool problem. You can try doing this on LeetCode. It's on there. Okay. So all right. So that's divide and conquer. I'm not gonna cover too much about this because that is like in the that's actually in the previous that because that's in the previous half of the semester. I'm gonna now deal with NP complete problems. So something about NP and NP complete problems. So so far we have seen like certain problems where we can solve using polynomial time denoted by p. So polynomial time may include something like O of n squared, and so on and so forth. Now, oh, right, I forgot to zoom again. So this is what I wrote so far, okay? So NP complete problems. So far we have hang on, I'm gonna need to deal with this. That was a Microsoft Word thing. So far we have solved some problems that that are in polynomial time, meaning we have O of n time, O of n squared time, and so on. But sometimes you have oh, actually, you would say that ln n might count as part of like the p type problems. Basically, something that's pretty nice and efficient in terms of time. But NP problems might actually deal with algorithms that can be efficiently verified. Like you can verify the solution very easily, but not solved as easily. So basically, you may have like something as crazy. So I'm going to write down this one: non-deterministic polynomial time. So for this one, um, for this one, for this one there are different examples you can look up. One is called the traveling salesman problem. The other is longest path. You've seen this in lectures before, right? Like longest path. Uh, you might have something like integer. Is it integer linear programming? Well, something like that. Yeah. So ILP, but this is the integer variant of linear programming. I'm just gonna call it integer linear programming. Okay, something like that. And then you might also have uh, independent stat on graphs as well. So I'm going to just start my list of examples here, but like you can look up a whole lot of these. Like you can look up like those on the lecture notes. Um, and these are not easily solved. They are pretty hard. Um, and And these and we still to this day haven't like even answered the question of uh whether whether we can like solve even of these in polynomial time. So maybe the set of polynomial time algorithms is the same as like the NP type of problems. Who knows? Like we still don't know. And whoever can prove this can actually win $1 million. So I don't know. You can just do what you want with that. And I'm gonna show you like how we visualize P and NP sets of problems. So here's what it looks like. So basically, this is blurry, I know. This is blurry, but this is actually what I can do for now. So basically, for the case where like we disproved that P is not n equal to NP, it means that there's this region where where like P where like where like the p-type algorithms or p-type problems can't even where like p-type problems can't even help solve those np type of problems. Okay, so let's see. And of course these of course there are also problems where like if I can solve like one problem like A, I can also solve the some problem some like supposed to be a hard problem B. In that case, we have the notation A reduces to B, and that means if A is easy, then B is also easy. Okay? Um, and of course the inverse is true. So if B is easy, then so is A. And of course, if A is hard, then B is also hard. Okay? Assuming that P equals to NP, you will in that case like in all the C of C like SEA in this ocean of NP hard problems, we might be able to solve a subset of it using by solving maybe a variation of a problem that's supposed to be an NP type of problem. And that would be how I interpret it. But do feel free to clarify that in the chat as well. But the notation for A reduces to B that might be useful to see. Um, and that's all I can tell for now. We are at like the time is at 8:50. Okay. Another thing that you might want to know in the list of in the list of in the NP complete problems is the independent set where like I'm gonna where like you want to have a set of vertices that are not adjacent to each other. For example, if I have something like uh, something like this, well, you may color something like this, this, and this, And in that case, so that's one independent set. You might also, if I can redraw the graph, you might also have a set that looks like this. You may have this, and then you may have this and this. Basically you can move this one up there as well, and so on and so forth. That's an independent set, where like you're given a graph, and then you're going to tell me, like you're gonna give me a set of vertices on this graph, where each where like all the nodes won't be adjacent to each other. So this is really useful in a whole lot of like searching problems that you see as part of the NP problems. By the way, is my like, oh, okay, good. I'm going to paste this. So here is something that I find really useful in the lecture in the lecture notes, where like we see like which problem is reducible to what. All the and you've already known this perhaps, but like all the if I can even like remember how I should say this, like there's also one type of problem called the satisfiability problem. I would just like let you I'll let you like study that on your own. But all these NP all these NP problems, they reduce to the satisfiability problem, which then can be reduced to the three sets, which means you're dealing with only three, uh, with like three variables. If it's not variables, then it's just three things. Otherwise, there will be a three in it. And then the three set problem may reduce to the independent set problem, uh, which uh, which can reduce to the vertex cover problem as well. Like I'm going to like skip over a couple of these because I just want to make sure like we're not too short on time. We still have four more things to cover. So yeah, NP problems. Some problems can't be solved efficiently, but they can be verified efficiently instead. While the others, it might be just the inverse. Okay, the inverse of whether you can verify them easily or whether you can solve them easily. Yes. Okay, so that's pretty much what I want to talk about in the NP type problem. Oh, just going to fix this because I don't want like some things to like uh oh, hang on. I just don't want like certain words to like bleed into my like other concepts. Okay. So that's NP types of problems. Feel free to ask me more about it at the end of the tutorial, because we're gonna move on to the next one, which is network flow. Let's see if I can align my stuff properly. Okay, network flow. So for network flow, I'm gonna give you a graph, okay? I'm gonna give you something like this. And then I'm going to do this. Like for example, I'm going to give you something like this. And the thing about a network is that let me zoom in here. The thing about a network is that a network has some kind of value and a capacity, basically a maximum of the value. The value could be like the size, the size of your traffic going through the edge, and so on. And you may have different types um, of capacities across the entire graph. Okay, something like this, for example. Oh, there's one more. Okay, so something like that. Now, there are two specific problems regarding networks that we have dealt with, and it and these they are the min cuts, and the max flow problems. The min cuts, basically, we're gonna split the graph into like two disjoint sets of vertices, and then we're gonna find a cut of minimum capacity. Or is it capacity? Is it capacity? Uh, let's see. Yeah, it's minimum capacity. Basically, for example, I want to get from like from S to T. I want to split. I want to split my I want to split my network into two, well, quote unquote halves, where like the capacity going from the S half to the T halves. The S half is the set that has the S node, and the T half is the one T that has T in it. So the out the outgoing edges, like these ones over here, can have a minimum capacity. Okay, so that's one problem you may want to solve here. Another problem you may want to solve is something called the max flow, where like we assign edge values uh so that you have a maximum amount or a maximum number of things flowing through the edges overall. So, and that is what we call flow. So that we have a maximum flow. Let's see if I got that right. Flow, and and of course oh, maximum. We have uh, across the network. I'm not sure if I no, I'm not sure if like this is clear enough, but pretty much we're gonna assign like some values into these edges uh so that we can we can have a maximum amount of things going through all the edges, not just one edge, all the edges. And we might need to find a basically we may find a path that helps us carry a maximum number of boxes. Okay, so that's about it. Okay. Oh, actually, I missed one over here. Okay.
Is it okay if I ask a question right now?
Yes.
Okay, because I try to look at this graph. I think for the min cut, I'm trying to look at it right now, but I think that what you have at the start, like what you have at like the source, the
Mm-hmm.
value is not the same as what's in the sink. I think no matter which edge you see it,
Yep.
because like I kind of added up some of them, so I get like 23 on the source and like something like
Mm-hmm.
29. on the
Oh
sink.
yeah.
So I don't know if like that's gonna if that like makes the problem wrong, or if that or if it still
Mm,
makes it a valid problem to like actually solve.
yeah.
Because like
Right. I will.
examples in class, like in the example in class, like I noticed that the min cut, sorry,
Mm-hmm.
and for the min cut,
Yep.
the capacity at the source is also should be the capacity at the sink. So like they should both be the same. I'm assuming.
Oh, okay. Yes, my apologies. Okay, so in that case, I'm going to switch up the values here. I'm gonna change this to 5. Does that does that make it okay?
I think so. I still have to check to see if they
Yeah.
correlate.
Yep. So
I
yeah,
just assume they do, I guess.
yeah. Okay, so I remembered, so in that case, yes, I checked and yeah, so yeah, sorry about the way I like made my network. I wasn't aware of that constraint. So basically the edges going from the source, if you sum up the capacities, they should have the same the same total capacity as the edges that directly go to T, which is the sink. Yes. Now that I realize, yeah, that would make more sense. That would make sense for this type of problem. Yes. Thank you for clarifying. And yeah, sorry about the mistake. I wasn't aware of that. So, um, in the labs we have worked with an algorithm called the Ford-Fulkerson problem. The Ford-Fulkerson algorithm, and that is where like we try to find something called an augmenting path, meaning some path that can go from S to T, while still not going over the capacity of all the edges. So basically, I'm going to draw a much easier network because I don't really like the one I drew. So I'm going to draw one that's easier. So I'm gonna take one that has something like this. I'm gonna take I'm just gonna draw 4 nodes. Something like that, and then I'm gonna do something like 75, 125, uh, and then this one is 80, 120, and then I'm going to do 50 here, for example, and I'm gonna go from the top to bottom. I'm going to scroll my camera now in case I need extra space. So what we do here is that I'm going to find a path of going from S to T. Okay, so how about going from S, take this path, uh, and then I'll perhaps take this path, and then take this path, something like that. So that's one augmenting path. You may also take like the right side, and then the one at the bottom, and then the one that goes to T as well, and so on. So basically, we're just gonna find any augmenting path that exists, and then I'm going to compute the bottleneck. Okay, in our case, the bottleneck here is 50. In case unless I just got it wrong, uh, and I'm going to assign 50 to our edges that are part of the augmenting path. It means this will be, so 75 minus 50, we still have 25 left. 50 minus 50, we still have 0. Um, let me see if I can like remember that. And then oh, actually, what am I doing? Okay, 0. So this I'm gonna assign 50, and then so this 80 will turn to 30. So basically, we still have 25 left in the capacity. The edge with 50 on it will be full. The edge with 80 on it, we still have 30 in the capacity. Okay. Okay. So we have the first path. Then we're gonna keep finding the path. We're gonna keep finding any augmenting path that exists. Uh, for example, I'm going to maybe pick 125, and then for example, let me change the color. I'm going to use 125 and then 80. We're gonna take that 125 and take that 80. I'm going to calculate the bottleneck. So now, I'm going to now I'm going to look at the bottleneck. The bottleneck is actually 30 in the past because 30 is the smaller one. So I'm gonna add 30. So now this will turn to 0. And then I'm gonna add 30 on the 125 edge, which basically gives us 95 left. Okay. Um. Yeah. So anything to be clarified here? Anyone? Like in case I made any mistake here. So I'm gonna keep on finding the augmenting path until we just can't find one anymore.
Wait, so now you have two augmenting paths, right? Is the third one just gonna be on the left side, 75 and the
Mm-hmm,
120
mm-hmm.
weights?
Yep,
Okay.
yep. So now we're going to so basically we now have like so now have two edges that are full. Notice that the 50 and 80 edges are full. So we cannot take those anymore in our subsequent augmenting paths. So now let's add one more augmenting path going from S to T by taking the left side now, which is going from S to the one that has 25 on it now, and or the one that was originally 75 in capacity, and then we will take the 120 capacity as well. In this case, uh, the bottleneck here is 25, so we're gonna add 25, which reduces the capacity back down to 0, and then we're going to take 120, and this will be added by 25, and this will give us 95 remaining as our remaining capacity. So basically, uh, if we run this algorithm again, we can try to get an augmenting path, but you'll notice that there is no way we can even get to an augmenting path anymore. There's no way we can even get from S to T anymore because all the edges we need are full. Okay, so once we're done, once you're done running your iterations, can you not do a backwards edge from 125 side 50 and then 120? Wait, hang on. 125 and then 50 and then 120. Oh, you can do that. Okay. Oh, right. I forgot that you can actually do backward flows as well. I I thought that is not how backward flows work, but yes, you can actually do that. I'm gonna color this in blue, okay? So now, what if we do a backward flow from 125? So we take 125, take this and take this. So in our case, the bottleneck is still 50, but now, um, we're going to reduce the value by 50 because the bottleneck is still 50 though. Because the rest will still have 95 left, but we still have that 50 which we have subtracted in full. So we're gonna add back the 50 to give us 50, and then um, and then the other ones we're gonna add 50 to it. So this will give us 45, and this one we add 50. This will give us also 45. Yeah. Okay, so anyone else can like find me another augmenting path? We're only gonna normally if we're gonna find augmenting paths, by the way, we should only take the shortest paths when possible. So the way I did it, it might not be an optimal way to do it. Yeah.
So to get the right augmenting path, you just have to like find all the possibilities, like of the source, like of the source going to the sink, and then you select the one where all the goes past all the nodes and gives you the maximum flow. Is
Yep.
that it? Okay.
Yeah. That. Yeah. Um. As long as we have an augmenting path, we're not gonna stop until like we don't have one. And like normally, if we find all the augmenting paths, chances are we won't be able to even finish the algorithm at all. So a lot of times, we only pick the shortest path, and you can actually do that by using BFS. Okay. I normally would just pick the shortest augmenting path using BFS as well, just so that like it can be convenient and we can end the algorithm faster. Yeah. Um,
Uh, is it okay if I can ask one more question?
Go ahead.
It's just in this one, like I was able to keep up with you until like the first two like augmenting paths, and then after that, I'm not really sure where you like how you were able to get the values and everything. That's just a little confusing.
Yeah. Yeah. Do
If
you
you
need
don't have
help
enough
with
time to like,
yeah.
if you don't have enough time to answer it, can we just do this? Can you just like answer at the end of the session? If
Sure. Just I guess like it's something related to finding the bottleneck actually. Like
okay,
in the past, like which edge gives you the minimum capacity, like the minimum available capacity. Like you need
I
to
see.
find that in the path that you chose for your augmenting path that you chose, and then you're going to add or subtract depending on like what flow you're working with. By that specific minimum capacity. Yeah, so that's what the bottleneck is. Yeah, if you need to know about that, we can talk more about it later. Like I will stay a little longer after this session. Okay.
All right.
Yeah, yeah. All this is also confusing to me too, so I sometimes need a little more help on this one. Um, the only time we did the forward focus on algorithm is the ones without any backflows at all, because basically there's something called the bipartite partite matching, where we try to match candidates to jobs, right? Remember that? Basically, I'm going to match maybe four candidates to three companies. One candidate has this. The other has all three offers. Wow, lucky them. One only has one, and the other has this. Now, this network is very, very confusing, but feel free to maybe draw your own as well. And these companies will go to a sink. So we have a source and a sink. Okay. So uh, this is bipartite matching. Uh, I think the last time we did bipartite matching, all the network flows only go one way to to make things easier. Like all the network flows go one way only. Okay? Like all the augmenting paths go only one way because that's how we can that because that's the only way we can reach from S to T. And you can use the like Ford Fulkerson algorithm to get the like a maximum number of matches you could do with the with like when you're trying to match four candidates with three available offers. In our case, it should be just three because we could do one here. For example, we could do one uh here, and then you could do one here. Like so that's one example. You can find just try to find or DFS your way through all the augmenting paths and try to see if three matches is what you got. If it's not, then like do let me know after this session on like what it actually is. So feel free to work on this as well. But bipartite matching that's one application of the this is always at the end. Can it also be this way? I'm not. I actually think most likely you'll be given a end to end. For example, if I have like something like this, maybe something like that. So it might be something like this. Maybe like maybe the company didn't even give out any offers because like the candidates are not what they're looking for either. But I'm not sure if that will make sense in a network. I think it should, as long as like we have four edges connecting S and four edges directly connecting to T. But maybe I can draw one. Maybe three got the offer. Only three got the offer. Then in that case, I can let three take that one. Yeah. So I think most likely end to end would be like let me take a look. Um, I think most likely you would I think most likely it would make more sense to do end to end, like same number of candidates and same number of companies. Yes. Okay. Yeah. But make sure you look at the lecture notes. I looked at the lecture notes, and yeah, a lot of times we are given like end to end matches. So I think we might be only working with end to end uh matches here. Yeah. So in that case, I would just do it like this. I would just give you like this, and like you can match like a maximum of four in this case because we have enough because like most likely the candidates would be satisfied using a combination like this, for example. But you can also try other combinations of matches as well. Like try other matches as well. See which other ones you can come up with. So that's
Wait,
bipartite matching. Yep.
sorry,
Questions.
sorry, sorry. Very quick. How do you go about solving these again? I wasn't really paying attention to that part.
Bipartite matching, just like any other network flow problem, maybe try solving this using the max flow problem. Using the max flow
Yeah,
problem as your quote unquote template.
like the using the Ford Fulkerson algorithm.
Yeah, use Ford Focus. This is
Okay.
literally what we did in the lab.
Yeah, I know that. It's just like I tried solving it manually and I kind of forgot how to do it
Yeah,
as we discussed.
it's Ford Focus. Maybe assign all the uh try this. Like I'm not sure if this should be assigned 4 or it should be infinity. I assigned the edges connected to S and directly connecting S and T like with infinity, but you could I guess like you could also do just 4, and then you can assign all the other edges with 1. Like all the edges, all the messy edges in the middle, they get assigned only one capacity because maybe only one company can take one offer.
Right. Okay.
Yeah,
Thanks.
yeah, no worries. Okay, so that's how you do it. Oh, so NP, so the problem becomes NP hard if it's M to N, or that the maximum bipartite breaks in the scenario we don't have an equal amount. Hmm. Well, I might need to look into more. I might need to look into the lectures for that one. But yeah, a really good question. And a really nice food for thought for me because it looks like I need to study more on that front. Yeah. Okay. I'm going to like stop myself here in the network flow concept because I want to now move on to substring search. Okay. Um, if you all have like extra questions for me, let's save it until the end of the session where I can like spend a bit more time answering extra questions. All right. I'm going to move on to substring search. So now I'm going. So that means I need to do some nice scrolling. All right. Let's see where I put up my substring search. Okay. So this is substring search. Okay. So in substring search, I'm gonna give you maybe a some text. For example, I can give you some text like "Hello World." I'm not gonna add quotes because like I guess at this point you should be able to implicitly imply that you're gonna be given a string. And I'm gonna give you some pattern I want you to match. For example, hello. A lot of times the patterns are case sensitive. Okay, unless you're working with something like equals ignore case, then sure, then you don't have to deal with cases. But a lot of times for patterns, they I assume them to be case sensitive. But if they are not in in the lectures, then like you can go along with like case insensitive cases. Okay, like case insensitive situations. So I want to know like where does the pattern hello occur in the text hello world? Like which index does the pattern hello begin? I think you know the answer already. It's index 0. Okay? So these two will give you index 0. Yep, there you go, Vishnu. Good job. Yeah. Um so for that one, um so basically you're gonna encounter like similar situations. You can even uh remember that like some remember that like maybe the same pattern can like occur in the uh uh string like multiple times. For example, if you can do Baba, in that case, I might even you might want to even list out all the indices that where the pattern occurs. In our case, here we have index 1, which is this one, and index 2, which is this one. Or actually, no, that's not index 2. That's index 3. Sometimes you would want something like this. Um, see if you can like see if you are able to like identify the same thing. If you don't really agree though, then yeah, maybe try to see which um then do let me know why, I guess. Of course, if you don't want to list out the all the matches, then maybe a lot of times you might want to find the the very first time this pattern occurs. In that case, you would just return 1. But if I want all the matches, 1 and 3. Okay? So those are examples of substring search. There are different ways you can do substring search. One is the deterministic, and one is the deterministic finite automata, or DFAs for short. Actually, the singular form of automata is automaton. Okay. So basically, this is literally just a state machine. Okay. So for example, I want to match. For example, Uh, I'm going to build a state machine of the pattern like B A C. Okay. In that case, I'm gonna draw some states. So state zero means we have zero matches right now. We're trying to match the zeros. Uh, and then one, two, and then we have matched all three. Then three will be your goal. In that case, our transitions, the correct transition, the right path should be following taking the transition B, A, and C. So if we find B, A, C in that order, we're good. But sometimes we might have but sometimes if you're searching a string, well, actually most likely like oftentimes when you're searching a string, a given text, you might encounter some other characters that are wrong. For example, at state zero, you try to look for B, right? In that case, we shouldn't find A or C in our current character. In our case, we will make a transition that loops back to in our case, at state zero, we're gonna loop back to state zero if we find the wrong character. It means we're on the wrong thing. And then at state one, we can try what happens if we find so what happens if we find B, for example? If we find B, in that case, it might potentially be the first character in the pattern we're looking for. So let's just loop it back to one for now. But what about C? Well, that doesn't make any sense, so we go back to zero. Okay. How about uh how about state two? Well, state two, if we have A, then if we're given A, then in that case it wouldn't make sense to it wouldn't make sense to the pattern either. So I'm gonna draw a transition that goes back to zero. But what about B? In our case, we're gonna go back to state one because that might also be the first character in the pattern we're looking for. And finally, we have C, which is our end goal here. So basically, DFA would involve making a state machine that covers the transitions of all the possible letters you can find in your string, and we're gonna map them to like a the resultant states number in each letter, well in for every state. Okay. Oh, let me also mark the zero as the start. Okay. Yeah. So that's DFA. Although if you want to learn how to build the DFA using a matrix, you can actually look at the lectures for that. You can look at the lecture notes for that. Uh, there's you can actually if you do it right, you'll be able to build the DFA in linear time. Yeah, and there's a way to do it. So you can look at that and see if you can understand that. Uh, so I'm gonna now move on to two other ways we're gonna try matching strings. Not sure if they are DFAs, but I know that these two algorithms are pretty good in their own way. One is the Boyer-Moore algorithm, where we try to skip characters depending on whether like our missed our missed character is in the our wrong character is in the pattern or not. So furthermore, furthermore, there are two like implementations of this algorithm you can look at. There's the good suffix heuristic, and there's also the bad character heuristic. So the one that we did in the lab actually, or actually the one we covered in the lectures is actually the bad character heuristic. The good thing about this particular implementation is that it's easy. It's easier to do compared to the good suffix heuristic, and it's implemented the most. Some programming languages do skip the good suffix heuristic because it's really hard to implement, and for two, it the gains of implementing it are not really huge. Also, let me go and turn on a fan because it's getting hot here. Okay, so for the Boyer-Moore so that's the Boyer-Moore algorithm. Basically, in the bad character heuristic, you try to compute a you try to compute a skip table. Basically, for example, like we if we match an A, we're gonna uh so let me go ahead and like give the pattern of B A and B B A C A B. Okay, something like that. And we can only have A's, B's, and C's. Okay, so for example, in this example, we're gonna calculate the skip table using by taking the rightmost index of our pattern string. That would be like the number of characters to skip in case we encounter some specific each specific character that is wrong. So in first A, the rightmost would be 0, 1, 2, 3, 4, so that would be 4. B is 5 and C is 3. It's like we just take the rightmost here, the rightmost index of each character in the string. So that's the skip table. And then afterwards, you're gonna skip by and afterwards, when you let me BBACAB. Okay, so when you try to match the text with the pattern, and you try to for example first match the first six. Do note that like normally you would like scan from right to left. You scan from right to left, but notice that like we have B, which is wrong. And looking at the skip table, we're gonna skip 5 times. 1, 2, 3, 4, 5. Actually, no, this is a little wrong. Actually, no. We need to take if I can like look at my substring search notes. Um, we need to take um we need to take in the Java implementation, we are actually taking the maximum of 1 and oh, actually no, we're doing this wrong. Okay, so we actually start scanning from right to left, right? So pretty much we start from j equals m minus 1, so this is the initial j, and like we're gonna keep going until oh, actually no, this is wrong. This is right there. So hmm, okay, never mind, never mind. I was doing something wrong here. We're gonna go from I. Uh, so in the Java implementation, if you look at the lecture notes, we start a counter I that has that goes from 0 to n minus m, which is so that's 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's 10. Like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 10. So we go from we let I loop from 0 to 10 minus 6, which is 4. 0, 1, 2, 3, 4. Actually, wait. 0, 1, 2, 3, 4, 6. Okay. So we loop from 0 up to oh, actually n is 11. Sorry. N is 11, m is 6. So that will be looping up to 5. Okay? Yeah, there you go. That makes more sense. So we're going to start by letting j by having j be m minus, j is gonna be so I'm going to write down a the matching the matching situation here, b b a c a b. So we're gonna start j at the end of the at the end b, but this is wrong. And but this is wrong, right? So in our case, oh, what happened here? This is wrong because B is not A. So what we do is that we're going to look at the skips table here, and we have determined that so the okay, so we have determined that like the right character should be A. So how many do we skip? We look up uh we look up the skip table using A as the key because A is the correct character. We will skip by 4 in our case. So we're gonna get skip to be 4, and then we're going to look at we're gonna then look at like the other characters. Um, we're gonna look at the other characters. Oh, let me use blue to denote skips. So at B, at B, we're gonna try skipping using A as the key, so that's 4. And then to the left, we have A, but it's not B. So we look at, but it is not B. So we try to skip using the skip table at key B. Then in our case, this is 5, but that is pretty much but so that means this is 5. And then we're gonna keep on oh, we got oh, so that's j. Oh, so it's j minus, okay. So j is 5 here. So let me try it again. So 5 minus 4. So basically we're gonna offset by 1. If you so I was just looking at the Java implementation of this. Yep, 11 minus 6. Yes, that's 5. Thank you. Thank you, Gianmarco. Um, Gianmarco. Okay. Okay, so we have so just like last time. So looking at the Java implementation, the skip here is equal to the maximum of 1, and j minus the right side table at the character at the character that's supposed to be in the pattern. That in the oh actually no. The text dot char as that is like the character in the actual text that we're looking at. So in that case, we're looking at b. So that means this should be 5. So 5 minus 5 is 0, but we're gonna take the maximum of 1 and 0, so that is 1. Okay, so let's look at the next one. Here we have a, but but a but a here is a here turns out the actual text is b. So b here oh actually wait, hang on. Text char at, yeah, okay. Ugh. All right, let me clarify this again. So we're looking at text dot char at a, this a, and yes, the lookup does say 4. So let me go ahead and like correct that. My bad. Okay. So we have um so we have a which maps to 4, which means that's a max of 1 and 1. That's 1. So next we have b, which is 5, which because this is wrong, we're gonna look at b in the skip table, and that maps to 5. So that is 5 minus 5 is 0. 5 minus 5 is 0. So that makes 1 max of 1 and 0, which makes 1. So here, the next one here is c, which is uh, which is pretty much is wrong because the text here is b, which also maps to 5 in the skip table. So same situation here. The next one is a, where but because a match got a match here, we're going to do. Oh, actually, wait. So we have 5, 4 minus 5. Okay. All right. Actually, I messed up quite a lot in the execution of the algorithm. When you're in the exam, please don't be like me, okay? So here, let me try that again. So at j equals 5, we got a that maps to 4. So that is so j here is 5, and the map tells 4, which gives us 1, 1. Okay. Next j here is 4, and but we have a b, so the skip will give us the skip will give us uh the skip will give us 5. The skip table gives us 5. In our case, our current index is 4, but we subtract by 5, which gives us -1. But the max of 1 and -1 is still 1, so we're still moving by 1. And then same thing for the case of C. We got 3 minus 5, which is -2. Uh, like this, but the maximum is still 1. A is skipped, B is skipped, and then finally we have A skipped, B is skipped, and then we finally have B mapping to A, which also maps to 4. So we have 0 minus 4, which is -4. Of course, the maximum is still 1. So we're going to skip by 1. It means in the second iteration, we're going to map this one, B, B, A, C, A, B. And what does this give us? Well, here, this is not going to match very well. because first we have the C here. We have this is 6 minus 3 is 3, and then um is 3. So this is C is 3. 3 C maps to 3. Um and then uh the next one, A is a match, so we're good. B, so B, well, we got a C in the pattern, but we got B in the text instead. So we're gonna look at the current text. We have a B, so we have the skip table mapping to 5. So in that case, we have 3 minus 5, which is -2. But that means we need to skip by 1 again. Okay. How about A? Well, we're matching with B here, so we still have 5, and we have so in that case, at J equals 2, 2 minus 5, we got -3. Well, it's still 1. And then we have a B matching with A. Well, A maps to 4, so we have 1 minus 4, which is still -3, which maps to 1. And finally, we have B matching with B, so we're good. So we need to skip another 1. Let's skip another 1 more time. We have right, B, B, A, C, A, B, and I'm going to like skip computing this one because we're running out of time. Um, so in that case here, I'm gonna look at how much I'm gonna skip. So first, so here B is matching A, so this is wrong. So this is 5, 6, 7. So 7. So we got 3. Okay, so C here, this is 3. 3. 7, 7, 6, 6 minus 3. It's still 3. Um. Okay, so how about C and A? 7, 6, 5. So this is 5. This is like 5 minus 4. So we have 1. And then A and B. So this maps to 5. 7, 6, 5, 4. So 4 minus 5 is -1. So that's a 1. B and C. Uh, oh wait, actually no. B and B they match, but B and A they don't match. So we have 4. So this one is 2. So 2 minus 4 is -2. So we have skip equals 1 again. And finally, we have B, B, A, C, A, B. And actually, if you try computing this, um, you'll notice that like all these will be passed, meaning we won't have a skip at all. So that means we found a match. Okay. So normally, if you want to return only a true or false, where like the boolean determines whether you got a match, you stop here. Otherwise, you might as well just keep going, like move one to the right and keep matching. So let me do 4. Okay. So I'm going to now do there's one more way you can do this, and it's called the Robin Karp algorithm, where you do hashing, and then you match the hashes. Match hashes, and then if you have a match, then you just match the substrings. Okay. Um. Oh, actually, so here is the Boyer-Moore execution here. Just so that y'all can see. Okay. So I'm gonna now move on to linear programming. I'm not gonna talk too much about it, because we have covered kind of because like there is no time. So linear programming is that I'm gonna give you a series of a linear system of inequalities, something like that, and then you just I'm gonna do one more. Um, like something like this, and then you want x and y to be bigger than or equal to 0. So like so what solution would you so what solutions can you do? And can we maximize, and at the same time can we maximize 2x plus 3y, for example? Like you'll be given a some kind of like a system of inequalities, and you want to maximize some separate objective function. So this is the objective function. Okay, so in that case, so to you can actually visualize this with visualize that with a polygon. I'm not gonna draw the polygon. I'm not gonna draw the polygon though. It would be nice if I could have the time to, but basically you might want so basically you put it to standard form, all the equations with slack variables. Basically, the slack variables are kind of like the offset. That will make that's came from the inequality. Like are you gonna subtract or are you gonna add to fulfill the uh, or are you gonna add? Like we don't know. Who knows? And then we're going to so after we put our equations into a standard form, uh, we can find extreme points, and then we're going to, so when we after we put after we put stuff into standard forms, we're going to now basically you find the extreme points. You might as well just plot that actually. You just plot that on a graph, and you might get yourself some kind of polygon, something like this. And then underneath it is the convex. So this is the convex polygon, and this is an extreme point, something like that. That's just the example. So you gotta find the extreme points on that polygon, and we're gonna we're gonna pivot from one extreme point to another until we find an optimal solution. Okay, so you go from like one pivot point, then you go here, and then we go here, and then we go here. But at some point, you might want to stop, because the only way we know how to stop, when to stop, is if the so we stop if the slack variable coefficients. Let me check. Yeah, if the slack basically if the objective function, which should have the slack variables inside it, um has only negative or zero coefficients, then we stop, because that means we found that means the objective function should return the optimal solution. Yeah. Yeah. You can look at the lecture notes for that one. Uh, Let me finish writing. So that is that's when to stop. Okay. So that is linear programming. This algorithm is called the simplex algorithm. And I know that like this particular algorithm might will be on the exam, so I'm just gonna briefly cover that. And finally, for the last 3 minutes, I'm going to cover randomized algorithms. Feel free to ask me some questions like at the end of the session, because I like I said, I won't be able to cover everything. So I'll do what I can, because I too have some things I need to work on as well. So basically, randomized algorithms, you can basically you're gonna make an algorithm that involves picking something at random. Like you might as well just roll a dice or something. I don't know. Like I don't know. This is a randomly laid out dice. Okay. So we have algorithms that involve like some kind of roll of a dice. Um, one algorithm like uh the reason why we might use randomized algorithms is because they lead to a simple the simplest algorithm, maybe even the fastest, or it might be the only one. Like it's simpler, it's faster. It might be the only one as well. Who knows? But it doesn't have to, it won't be 100% accurate. But we always try to make it as precise as possible. So earlier in the earlier when I covered the Robin Carp earlier when I covered the Robin Carp algorithm, there are actually two variations. So one is so I'm going to just write down Robin Carp. One has Las Vegas. One is the Las Vegas implementation, where we have where it is 100% accurate, but it is not very efficient, because you have to check for the substrings, which might take a bit more overhead. And there's also the Monte Carlo implementation, where we don't check, just assume that it is correct. Don't check substrings. It is fast, but not. But it might not be as accurate. Okay. So the Monte Carlo algorithm is the example of a randomized algorithm. Another one you might have learned is involves something called a contraction, where you try to where you try to work with where you try to like turn this graph uh turn this graph into like just like a graph, a contracted graph with like two vertices uh by randomly picking a node, like pick a actually no, not a node, randomly picking an edge. I'm going to, for example, pick this edge. I'm going to contract this, and the others like actually don't matter because there's nothing else like connecting them. Then uh in another in another random roll of the dice, I'm going to pick I'm gonna pick this one. Actually, no, I'm gonna show you what happens when we have like parallel edges. I'm going to pick this one. I'm gonna contract this one. In that case, I'm going to use a different color. Why not? So in that case, I'm going to have a blue and a green. But now, because the rest of the edges are connected to the affected nodes, we're gonna move them to this new node like this. So now we have a cut between this and this. If I were to label A, B, C, and D, we have uh we have A being contracted, and then we have B, C, and then D left in the first step, and then in the second step we have A and D contracted like this. So this is what happens with contraction. You can run this many times in order to like reduce the chances of errors in your algorithm, and that's what makes it randomized. You have to basically keep running and praying that you get the right answer. But getting the right answer happens most of the time, as long as like we implement the thing right. Well, assuming we implement the thing right. So you can actually do contraction many times. I'm gonna show you like a really big. Um, just give me a moment. I'm gonna paste a really huge diagram of contraction like this. Just gonna wait until like I'm just gonna drag this over. So this is what contraction might look like. You might be familiar with that. You just keep on like running trials until you get the right thing. Okay? Okay. So with that done, um, you might also there are also a couple of things that I skipped over. So feel free to look at the lecture notes for those, because that is how I like got the things I needed to talk about. So with that done, it's about time I answer some questions. Just so hang on a moment, I'm gonna stop recording. For those who are watching the recording, I'll see you next time. Okay? Hopefully this will help you. No matter how big or small of a degree. See you.
Recording stopped.
Yeah. For those who said thank you very much. Have a good night.